I built Goderive, this code generation tool. I don't know. Can everyone see my slides?
Yeah, perfect.
Okay, cool. All right. Yeah. So I built this tool to demo what Go would look like with generics. So usually people do a presentation about a new tool they've developed, but today I'm presenting a tool I developed about 4 years ago, just before it gets, or just after it gets outdated, right? But this tool still has quite a few use cases that aren't covered by generics, and I think more importantly, some valuable lessons that this tool stole from other languages. So, for example, this tool also starts to touch beyond generics and towards higher kinded types. But I'll give you a little taste with a demo soon, and hopefully we'll have time so I can explain the subtitle and why the picture of the gopher has a blurred area. So maybe some of you would like to tell me some pros and cons of generics in the chat. So when you've used code generation, what has bothered you, or what has been good for you? Yeah, list duplication. Lots of extra code to generate code. That's a good one. Complexity testing. Oh, okay, yeah. Larger binaries, yes. You won't always know what code. Okay, yeah. And difficult to debug, yes, I agree. Only one person knows how it works. Okay. So that's a few. It's a pretty good list. So I think we actually covered most of these. So, but one that wasn't covered that I found quite annoying is that generated code is not always formatted. So you generate code and then you have to rerun GoFund over your whole code base, which can be hundreds of thousands of lines, which actually means it adds a lot of time to the dev cycle. I think you covered the rest. So I decided with this tool, I'm going to have some principles for my code generator, which hopefully addresses some of these negative aspects. So Goderive tries its best to generate readable code and be as close to the code that you would have written yourself. It also has to generate code that's already formatted, and this is weird, but GoFund code is easy enough to reproduce, so while you're generating code, so why not? And it speeds up the dev cycle. And yeah, it's obviously important to generate code quickly and to reuse as much of the generated parts to keep the compilation as fast as possible, because you don't want to generate big binaries. But yeah, that's enough ceremony. Let's get to a demo. Just need to do this. Cool. I can see the chat again. All right. So back in 2011, it was really hard to write the min function for Go. What is the minimum of two numbers? It was a question, and people would try to do this in one line. But I can also do this in one line. So I write just min of x and y, and I generate some code. And I can run it. I can see the min of x and y is 19. So what happened here is Goderive went over the code. It found a function that you are calling that doesn't exist. It was well, let me try to generate that for you. And it creates a file next to yours. And there's your min function, and it's commented, and everything. So that's pretty cool. But that with generics, that's going to be pretty easy. But what if you want the min of two structs? It's a pretty weird thing to want, but I mean, why not? Have the min of two structs, we generate some code, and we get Donna is the minimum. That's interesting. Why is Donna the minimum? Well, we saw that the input type was a person. So then Goderive doesn't just look at the name of the function. It also looks at the input types, and then it decides what function to generate. So in this case, it was two people. So Well, it's pretty complicated, so we can't just do a smaller than. So we have to generate a compare function. And we chose here to generate a compare function because then we might be able to reuse that with a max function, right? Yeah, and generate to compare an int is not really here. And okay, the function names aren't the best, but the rest of the code is pretty much the code you would have written, almost. Okay, but if we can get the minimum, if we can compare two things, why can't we just sort the list? So we can just sort me a list of people. And see, cool, there's Donna and Ron is second, right? So we have compare, so we can just use sort.slice to do this. Could have also done something that's slightly more efficient with the whole structure thing, but sometimes I also get lazy, so this is what I went with. And we always try to default to the pointer case, since this will be like the most probable thing that people will call for structs, since it doesn't actually copy over the struct, it just passes the pointer, which is just more efficient. Okay, so that's cool. And so this is like some sort of magic. And I spent a lot of time on this tool. And the only case that I ended up using in production was this one. And it's just to deterministically range over a map, right? Because this is not, at least 4 years ago when I was using Go, this was not ranging over a map was not deterministic. So I'm getting the keys from the map of people, and then I'm sorting the keys, and then I can range over this, right? Okay, so what happened is it looped over. It could not generate sort because it doesn't know what the input type is, because keys is also a function that doesn't exist. So it generates the keys function, and then it tries again. It says, now I know what the input type is, and I can generate the sort function. In this case, it doesn't use source.slice because that's not the code you would have written. You would have written sort.strings, right? And and it creates this list of the keys. Because everyone's still following. Like, I'm only watching the chat because that's the only thing I can see. 100%. Okay, that gave me enough time to take a sip of coffee.
Chat is with you.
Yeah, I can see. That's good. All right, thank you. All right, so that's cool. But so one of the things is I don't want this to be like too much black magic. Actually, the default way to use this is to prefix every function with derive, so that people know that it's derived, right? So before I passed in this flag prefix and passed in an empty string, but usually by default, in this case, there's no flags, and then you would have to type derive before each. And that's how I used it, because just a bit more obvious to people that it is generated code. Okay, now on to like my favorite use case. So in a lot of languages, we have memoization. This comes like from functional programming, where if you have a pure function, so that's like a mathematical function like addition, right? If you pass in the same numbers, you will always get the same result. There's no side effects happening or some hidden variable that's being used. So that means that if you call the function again with the same inputs, it might have been expensive to do this function, so why not memorize the result and store it so you can just look it up instead of recalculating the function. For example, in this case, with a regex must compile is something that we usually do in inits, but here's another way. So derive mem takes a function, any function that has some inputs and outputs, and then it returns the same function to you, like the same type, but it it has this memorization built in. So in this case, like the regex would be compiled, right? And so this compiling regex printf that I've put in here would only be called in the cases where I've not passed in the same R, right? So in this case, here we have some examples. So I have RE, so compile this regex ab.star, match it to the string ABC. So this will compile the regex and then match the string. Now I'm passing in a different input, so it will have to recompile the regex and then match the same string. I match a different string, and then now I'm passing in the same input I've passed in before. So I'm not going to recompile the regex. I'm going to use the one that I've compiled before, and then I'm going to match the string. There, you can see I've compiled the regex once. I've done the match. I've compiled the regex, the second regex, and then I've only done the match and not recompiled it. So you could have just written it like this, preferably, and then, yeah, we don't get any printfs. And it's really, well, it's not simple, but you pass in a function and you just return a function of the same type, right? That's what derive main does. So it returns a function that is actually a closure. So it has this map to memorize all the inputs and the outputs, and then it can look up in the map and call the function and store it in the map before returning it, or simply look it up and return it. Does that make sense? Cool. All right. So that does it really work? Here's Fibonacci, which is recursive. So it also works for this case. So here I have the function that I'm going to assign my memorized function to, that I create here. And yeah, this is just Fibonacci. And when you run it, yeah, it really works. And so if I take the derive mem away, this would be the same code, right? I've not actually waited long enough for this to finish in all the dry runs I've done. But yeah, okay, I'm not going to wait long enough this time either. But that's all well and good, but those were very simple examples. What about if I have two parameters and there's like one of them is a pointer? Okay, this is a horrible function, but just imagine you were calling some service and you only have to really look at the function signature here, right? So I'm passing in a first name and maybe I'm passing in an age, and then I'm maybe getting back a last name. And then I can just go, okay, derive name for find last name, and then I just call get last name on these functions. Let's see, okay. I mean, it will be horrible last names. I haven't actually run this. Oh yeah, so there, Ron's last name is TQP, and we couldn't find Donna's last name. And what's happening here is like, well, in this case, it's more complicated, right? So what we have to do in this case, we can't just use a map. We kind of have to hash our values. So we create a new struct that contains all the input values. And then we create an output struct that contains the input struct again, because we might have hash collisions and we want to double check. And we have our output value, right? So we create our map. When we have our input value, we call derive hash. So our generated code can reuse other generated functions to get. So this gives us the hash value of our input. We can look it up, and then we can range over all the possible outputs to just and check with derive equal if they're actually equal. And then if it's equal, we can just return the output. If it's not, then we have to call the function and append it to the map. So yeah, like it really tries to generate the code that you would have written. If we also look at this, in this case, we have like 2 inputs and 2 outputs. That would also work. But in this case, the inputs are simple enough so the struct can actually be passed into the map as a key. You don't need a hash function. Let me just get you back. Screen. Yeah, so that's a demo. Any questions? Except if that's Norse, it's just Go. Yeah, the Go types library is amazing. That's what I'm using in the background.
Yeah, very cool. And yeah, we use. Oh, sorry. Are you?
Yeah.
I thought you were done.
No, I'm sorry. Unfortunately, not. So yeah, so I learned. I actually got this whole idea from. No worries. I wasn't very clear that I wasn't done. So I got this idea for derived from Haskell, where you can just generate an equal, compare, and string method by simply like adding the statement below a struct. You just go deriving EQ ord for order and show for string, and then you just get these methods. You wouldn't have to worry about implementing them, which is really cool. But I wanted it to be really easy to introduce these methods for code generation to Go, but I didn't want to introduce extra syntax, and I also didn't want to use comments. I don't know why, but I had this weird constraint that I put on myself. So a little bit of trivia question for people on the chat. What do you think this double colon is called that is used before every type field? Cons? Oh, not in Haskell, but in other languages, yes. Okay, I can't pronounce that. That's a good one. Well, my base case is dolon for like double underscore, but it's not for like, yeah, double colon, because in Python you have double underscore, which is called dunderscore. But there's no name for it. It's just 2 colons. So anyway, I learned quite a few other things from Haskell. And just to answer Maurice Marcel, cons is I think single colon in Haskell, and yeah, double colon in every sensible language. So one thing I learned from Haskell is some error handling. So in Haskell, I didn't need to type if error not equal to null all the time, but I still got the explicit error checks. So that you can choose between exceptions or explicit error checks in Haskell. And I always, from Go, I want my explicit error checks. But let me show you like approximation I made with Goderive for this. So here we have some example Go code that it calls one endpoint to get an old user and then does a transformation to update the user and posts it to the new user's endpoint. So I'm going to get HTTP GET from the endpoint, then I'm going to read the body, I'm going to unmarshal, get the old user, then I'm going to translate to the new user, then I'm going to marshal, and then I'm going to post to the new endpoint. So we have a lot of error checking here, but we can also see that each function just passes its result to the next function. There's like, yeah, which is pretty convenient. So I'm going to shrink this a bit so that it compares to the Goderive code. Okay, so this is what the Goderive code would look like. It would simply compose these functions together, since they're all just passing their result onto the next function. So they're like a little bit of a pipeline. And this compose function just takes a list of functions and then just composes them so that you pass in the first value, get the endpoint, and then you get the result, which is the error. And how this works is basically a composed function is a function that takes two functions, a function from A to B and possibly an error, and a function from B to C and possibly an error, and then it composes these into a function from A to C. And then the generated code would simply do the error checking for us. But you can also just pass in as many of these functions as you want, and it will chain them all for you. And Haskell has like special syntax for this, so you don't have to call compose, and also like the functions don't have to be they don't have to chain as perfectly. You have a bit more flexibility. And I think Rust also has like convenient syntax for this with a question mark operator, but it doesn't use this underlying theory. It just does an error check. All right, so another thing, the function that was inspired by Haskell is like applicative do, and it's a whole presentation on its own to explain that, what it means in Haskell, but what it means in Go is super, super simple. And I'm sure all of you have written this function before, or a lot of you, sorry. So say you want to call two services, like one, this is a mock, right? So it does some expensive call and returns a string and an error. And you have another function that returns an int and an error, and you just want to do them concurrently. So you just say derive do, and they return you both results and the error, right? And just starts up the Go routines and waits on the error channel for the errors, and then returns you the results. So again, you actually don't need to understand this. Just know that it's happening concurrently. Yeah, and I actually learned like a lot of other things about concurrency in Haskell because it also has like these green threads. But it also, it's a bit easier to do like clean shutdown, or at least they teach you how to do clean shutdown from like chapter 1 of concurrency in Haskell. And I think this is also something like Erlang does pretty well. Okay, so final slide. So one of the hardest things to understand in Haskell is monads, and that's kind of the actual reason that I built this project. I wanted to explain monads to myself. So it's a lot of work to explain it to yourself, but that's what I did. So Haskell has generics, but it also has a higher level of generics. So when we think about generics, we only think about replacing, oh, sorry, I have to close this. Yeah. Yeah. So when we think about generics, we only think about replacing the types inside of our containers, for example, slices or channels with variables like A or B, right? But with a higher level, we can also replace the containers themselves with a variable, for example, M. So you might want to think of that like, say you have channels or slices, they're kind of the same, right? In that you can loop over both of them, and you could, like conceivably, not like practically, but conceivably you could write generic code that could handle either. That just loops, say, loops over the slice or channel and just applies a function to each element and replaces it in that channel or a list. Or yeah, something that just loops over and builds up some big result. This can, yeah, there's generic code could have handled either. It's just, you would have to think like each of these types would just need to implement some type of interface. And another example of this type of interface is a Kleisli arrow, which comes from category theory, but you can just think of it as the compose function. So category theory is like a whole field of math just about how to compose things. And it's quite important because or it can be, doesn't have to be. But just one of like the few ways we know how to solve problems is to break them up into smaller pieces and then to compose them back together. It's kind of cool that it is being studied how to compose things back together in a like good way. So in this case, the Kleisli arrow is just an interface that can be implemented for errors, for channels, for slices, to effectively like abstract error handling or a concurrent pipeline or a list comprehension. Because they're all the same thing. They all just rely on this simple function that just composes a function from A to B, a function from B to C to a function from A to C. And that's all that Monads is. But you can read more about that in my blog post, Monads for Go programmers. And then you can think of that as monads in Go or gonads. And that's why the image is blurred. And so there's a lot more functions in this list. And it's really easy to extend Goderive with more functions. I also didn't really cover how it handles duplicate functions in the code. So if you have two derived sorts of different types, there's this auto name flag that can rename one of them for you automatically, but I don't want to turn that on by default because, you know, I don't think people really like tools that edit their code necessarily. And then dedupe kind of does the reverse, where if you can't remember what the derived sort function was called, because you can add like some arbitrary suffix, then it goes and renames them to the same function, so you reuse as much code as possible. And that's my overview of Goderive and its gonads. Any questions? Now I'll open the question.
Thanks, Walter. That was great. And 10 bonus points for doing live coding and doing a live demo. Risky stuff. I have two questions, maybe just to get the ball rolling, one specific and one general. One of the functions, I don't know if it was compose or the one which just does things concurrently. It accepts a function that returns a string and another function that returns an int, and then it returns a string and an int. I think that might have been compose. And I was just wondering how you would handle two functions that return the same type in that case, or would it just be another return value? And or how would you, is the order deterministic?
Yeah, the order would be deterministic. So
okay.
Based on yes.
Okay, I see.
Yes. Yeah. Good question.
Actually, I don't think it is, because I thought in my head that there was that there might be a clash there, but they're separate return values and they're ordered. So, yeah.
Well, you got me. I think it's a good question.
And then my general question to you, and I don't mean to preempt my talk, but what are your thoughts on the generics proposal? Have you looked at it? What do you think about it?
I have to be honest, I have not looked at it.
Okay.
It has been like this was the last thing I did before I stopped writing Go, I guess. Yeah.
Okay. Yeah, I'm kind of sad because this looks so interesting, and I think would be so useful in a bunch of places. I think generics will make some of this easier.
Yes. No, a lot of it. Mm-hmm. I think actually, like, if you're trying to write generic code, I would use some of these functions as inspiration, because they are meant to be really composable so that you can create big things with only a few of them, because they're all inspired from languages that has had generics for a very long time.
Right. Thanks. We have a question from Marius. He says, is Goderive intended to be used during development and coding, or does it have application during build time as well, say on a Jenkins build server?
I like to check in my generated code, but that's I think that has been a debate in the Go community. So then I would say it's meant to be part of your dev cycle, and it does work with Go generate. Like that, I was still here for that, and So yeah, I just run it as part of my dev cycle when I used it. Yeah.
And just for interest sakes, we have a library at Luno called protocp that we use for copying the Go generator types that the protoc Go generates, to copy between those types and like our Luno Go types. And I think it probably does a lot of similar stuff to what Goderive does. But we had a spoke put in our wheel. Is that the expression?
Yeah,
sure.
yeah.
But because recent versions of the protobuf library, they've put this like do not copy interface into the type, so you can't do shallow copies, and you have to copy things property by property. You can't just say A equals B. If it's a Go type, you have to say A.A equals B.A. So actually, when Marius told me about Goderive, I thought we might be able to use it there.
Yeah, I think you can. Like, so there is a deep copy, a derived deep copy, but this would take two different types, right? Not the same type, but I think you can then like check that they're the same enough. And one of my pet peeves of copying over protostructs was that you wouldn't be able to detect that there was some new field, right? And then you would forget to copy that over. But yeah, I think in this case, you would be able to do that in like the Goderive step, where you would go to field for field, and it would be, I think, not medium level task to like modify deep copy to be able to handle this. And that's how I would start. I would copy deep copy.
Yeah, I probably shouldn't admit this in a recording, but we've had incidents because of that exact issue.
No, it's like there's no actual type checker that would check that for you. So, but yeah, you can do it with some linting, which you can do while you're generating the code. Yeah, and this is kind of why. Actually, we had exactly the same problem in 2011, and that is why we built like Go protobuf, so we could generate the structures that we actually wanted to use. But yeah, it's been too hard to stay up to date with the API version 2 changes. It's like that requires being paid to do it. Yeah. That would be a big job.
I feel you. Okay, I don't think there are any other questions.
Okay.
Yeah, thanks very much. That was super interesting.
Well, it's been great. Thanks for listening.